Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon, everyone. It's my pleasure to introduce Martin Johns. Martin came from Germany, and he is a PhD candidate who's expecting a PhD in just a couple of months.
Yeah, hours.
Yeah, so Martin is going to talk about secure code generation for web applications. Thank you.
Thank you, Han. Yeah, it's great that I'm here. So this is the outline of the talk. It's rather generic. I have like 3 slides to give you a bit background information about myself so that you know who's talking to you and what I've done before and where I'm coming from. Then we will have a brief look at the bug class of string-based code injection attacks, cross-site scripting, SQL injection, and so on. And I will try to show you how we try to tackle or how we analyze this bug pattern. And then number 3 is the main part. It will be we will have a second outline later where I talk about our solution or our proposed solution to the problem. Okay, so who am I? I have a strong background in software development. So pretty much until I went to university to go for my PhD full time, I've worked in a lot of different companies, wrote a lot of code, and pretty much all the code I assume was really, really insecure. But this background, at least I hope so, gives me a little bit insight in the mind of coders and what their requirements are and what they might want to use and what not. Then in 2005, I joined University of Hamburg back then, Professor Posiga's group, to work on the project psychologic. It was a research project funded by the German government and was investigating the state of the art in software security. And while my assigned focus was more in the C space, my interest rather quickly shifted into the application security space because there was so much going on with insecurities that were actively exploited and unsolved. After the psychologic finished, I was in a couple of short-time research projects with Siemens, with SAP Research, and right now I'm doing project management for a project together with Fraunhofer and other partners. So what have I done, what I'm not talking about today? I looked into mechanisms that should provide us with a second line of defense. So application security problems are rather frequent, and while there are approaches to detect such vulnerabilities, back when I started, there weren't pretty much no approaches to help the user or help the application to mitigate the exploitation if there's a security vulnerability. So I looked into cross-site scripting, cross-site request forgery, and attacks on the intranet, and looked into how does these attacks function, what are the requirements, and how are they executed in the browser and the application paradigm, and how can we change this paradigm in a backwards compatible way so that the attacker is not as almighty as he was before our approach. And also we did a couple of things in the space of detecting and preventing the application problems. So last week I was at AXAC and presented our approach on server-side detection of cross-site scripting problems by HTTP monitoring. So we took lessons we learned from intrusion detection, which is a rather mature discipline, and tried to apply it to cross-site scripting detection. Together with Siemens, we looked into static analysis and what the state of the art is there and how to benchmark such tools and what are the open questions. And also we did a preliminary project which led to the topic of today's talk on detection of string-based code injection attacks using a variant of instruction set randomization. But this is, if you have questions about those things, come to me after the talk. I'm happy to talk about those. So today I will talk about our approach towards language-based prevention of code injection vulnerabilities. Before I talk about how we try to solve the problem, we have to revisit the general bug pattern of string-based code injection and isolate what we think is the main root cause for those vulnerabilities. So if you look at the web application paradigm right now, you have usually you have a multi-tier infrastructure. And what's special about this, you have a heterogeneous amount of different computer languages that are employed by the application at the moment. So you have what we call native language. This is the language the actual application was written in. It's PHP, Java, C#. This is the language that does implements most of the application logic. And then we have a rather heterogeneous and large amount of what we call foreign languages. So those are computer languages, query languages, structured languages, general purpose languages, just like JavaScript, that are assembled on runtime by the native application to be sent then to external interpreters and to be executed or interpreted in the external systems, in the database with SQL or HTML in the web browser. And the main observation, if you look into bug track or full disclosure and stuff like that, this string-based code injection, which affects all sorts of foreign language assembly, it's always the same bug pattern, and it affects all. Every time some computer code is assembled dynamically within the native application, you're gonna encounter this bug pattern. And if you look at bug track, you see you're gonna encounter this bug pattern. So the types are cross-site scripting, SQL injection, shell injection, command injection, path reversal, XPath injection, LDAP injection, JSON injection. We have SMTP injection, and pretty much everything is susceptible to this injection tag. And it's always the same. How does it work? You have a dynamic code assembly, which is string-based in the current practices in our applications. And we're going to get some data from the outside through an HTTP request. And in this case, the password the user provided contains some unexpected characters. Those characters are blindly echoed into the resulting SQL statement. And in this case, this is the classical example for an SQL injection. What is the problem? Why does this happen? It happens because we have a mismatch in perception what is happening. The programmer, while he's writing his application, he has to interact with the database. He's thinking, okay, maybe he's even aware that he's actually writing computer code. But still he thinks, okay, I'm writing this SQL statement. So my SQL statement consists of a code portion. This is the static part. And I want to enhance this static code portion with some data values so that I can get the information from the database that I want. The problem is that the database interpreter has a completely different view on, let's call it, data and code separation of the elements. The interpreter interprets this foreign code statement strictly concerning the native foreign language's grammar. So it has a couple of code fragments within the statement. It has a couple of data fragments. On compile time, the string-based variable is unknown, whatever it contains. And so in our case of the code injection attack, so this is assumed by the programmer to be the data portion. But depending on which code comes in, there might be data in there, but also there might be fragments in there that are interpreted by the database to actually be code. So what is the problem? This way of string concatenation and string serialization before sending it to the database results in an implicit foreign code creation. So the programmer has to rely on the assumption that he's doing something correctly with saying, okay, this is the string, take it, execute it, let's hope everything is good. Okay, so we want to get rid of this. And our initial motivation was we wanted to look at how can we change the way we program our web applications in a way that on a programming language we're going to get rid of this bug pattern without to be too invasive. So I'm going to have a slide where I'll talk about the objectives. So we didn't want to invent a new programming language. We wanted to change the smallest subset of existing methodology to get rid of the bug pattern, but nothing else. So a general approach. At first we try to isolate what we consider to be the root cause of the bug pattern. And the root cause is, as I hopefully convinced you, as you probably already knew, that we use the string type, the dumb string type for foreign code assembly. And the string type, even if the programmer knew what he wanted to do, even if the programmer wanted to add his foreign code with some more semantical information for later processes to understand what his intent was with the string assembly, he isn't able, because the string is just a dumb sequence of characters, and therefore after the string assembly, everything is lost right now. Also, a second root cause, which is secondary, is that after this code has been assembled, it is transferred to the external interpreters, to the database or to the web browser through unmediated direct interfaces, and they just get the character stream and interpret it. As I already told you, we want to solve this problem on a programming language level. So our goal was that even but we wanted to force the programmer to write secure code, and so not to make a conscious decision. So the current practice right now is tell the programmer, okay, you have to sanitize your input, you have to make sure that everything is okay before creating the strings, and programmer fail at this. You can see this a bug track. Instead, we wanted to, as I said, change the general programming paradigm as far that if you use our method, you should be secure by default. Yeah, and so the question we had was, how do we need to extend or modify the existing practices to reliably prevent the vulnerability class? The methodology is then we try to remove the things that we consider to be the root causes, so that it boils down mainly to exchanging the string type for code assembly with something that is better suited. And as an afterthought also, we have to get rid of all those unmediated interfaces to the external interpreters. Otherwise, we would provide the programmer with a shortcut or a backdoor towards writing insecure code, even if you don't want to. So we want to have a reliable, secure system. Okay, our design objectives. As I told you, I have a background in programming, and I have interacted with a lot of programmers. And most of the programmers, they don't really like to change. They learned their stuff, they learned their languages, and they were really good in this. And therefore, even in the young field like web applications, they are rather reluctant to change the way it is done. Therefore, we didn't want to invent a new language. We wanted to develop a general concept that should be applicable with at least effort as possible for any modern programming language, at least or any modern object-oriented or procedural programming languages. And also, we didn't want to change the foreign syntax. If you look at special domain languages like SQL or XML, the syntax of those languages has been defined and created very carefully to solve a specific problem. By changing the syntax, we might willingly or unwillingly change the way those languages were designed in the first place, and this would also hinder adoption. And third, and this is also, especially when I've been working together with SAP for our practical implementation of our approach, programmers really like the flexibility of the string type. So creating, assembling foreign code with string type is a rather comfortable and a powerful method. So you can put the code together, you can rip it apart, you can apply filters on it, and you can jumble it around, you can index it. And so the string API has proven to be a very nice thing for programmers to create, especially non-trivial like big HTML pages and stuff like that. So all these design objectives that we listed before we started developing our boil down to, we wanted to keep the programmers happy so that we have at least a remote chance that somebody will use what we're doing. So taking our general methodology and our design objectives that I listed, we can isolate the three key components that we have to design, implement, and resolve. So for one, most important, we have to design and implement a new data type that is more suitable for foreign code assembly than the string type. We have to integrate this data type together with the foreign syntax in an unobtrusive way into the native code, so that the programmers will actually be willing to use our abstraction. And we need an abstraction layer which has an interface that receives this data type and then safely creates secure foreign code out of the data type that we send. Okay, so the main part of this talk, or the more interesting part of the talk, is devoted to the data type, because it's pretty much the key. It's the centerpiece of our architecture. We christened the data type because it was really awful to write blah 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 data type. We call it fleet. It's for a foreign language encapsulation type, and for our fleet we have a couple of requirements. It should be obviously part of the native language, and it also should be able to encapsulate foreign code of arbitrary length and complexity. So we aim to create a syntactic means to integrate to cover the complete foreign syntax and not a subset. That was really important to us, because otherwise we would still require the legacy interfaces for special purpose requirements. And third, to actually achieve the security requirements or the secure properties that we aim at, our fleet should provide strict separation between data elements and code elements in the foreign language. I will come to this, what we mean with a data element and code element in respect to foreign syntax. I will explain it a little bit later, what we mean. What we aim is that all code elements that are created on runtime by the native language, all foreign code elements, should be created explicitly. So with the string, as I said, with the string, all code creation is implicit. Take the string and think of it as code, and whatever is in the string should be executed. And there's no verification that the string really contains the code that I wanted to create. Instead, we want to get rid of this paradigm, but want to bring the programmer to say, I want a select statement. Not an SQL statement, I want a select statement which selects from a certain table with a certain condition. And I don't want a unit select in there, I don't want an update or anything. I really just want a select. I will come to this a little bit later too. Okay, before we come to the practical implementation, now a couple of slides on formal considerations. So we want to invent, or we want to extend the native languages type system. And we want to have certain security guarantees. So to have at least a guideline from the formal tool set that is given to us, we looked into type theory and how to model type systems. And we looked into prior work that used this, so we don't have to reinvent the wheel. So we looked into type systems, and the major thing that people do with type system security is enforcing confidentiality requirements. It all dates back to the Bella-Padula model, which probably everybody of you know really good. But for completeness' sake, Bella-Padula is this classic multi-level security model with two properties, and in the simplest case, two confidentiality classes, public and secret. And through these two information flow constraints formulated or formalized by those two properties, both direct and indirect flows from secret information to public places are prevented. Then Denning in 1977 showed that this can be enforced by static program analysis. And in 1996, Volpano and Smith formalized this approach using type theoretical methods and a type system, so that they could, by defining public as a subtype of secret, they could prove that if the type system is enforced on compile time, that those information flows don't work anymore. And there's lots of work that is built upon this paper. The dual model to Bella Padula is the Bieber model. It enforces integrity constraints and the confidentiality constraints by preventing flows from low integrity data to high integrity places. It works pretty much the same thing. It also has the two axioms for indirect and direct information flow, and it can be modeled completely analogous to. So you can basically use the same typing rules as with the Bella Padula model to enforce the system. So how could we this apply to our case? We can. So we said we don't want any code elements in our foreign syntax, whatever these code elements may be. We don't want any code elements in the foreign syntax to be defined by data elements. This can be abstracted into an information flow policy. So by defining the code elements to be of high integrity, I think this is a requirement that everybody could agree to. So when I'm creating code that should be executed, I demand that this code is of high integrity. And also we define data elements to be of low integrity. This is also, I think, totally understandable. Data elements can come from malicious people and dubious origins, so they should be of low integrity. So by preventing those flows from low integrity data elements into high integrity code context, we should be able to get rid of this bug class. Also, our problem that we have to solve is simpler than the confidentiality case, because we only want to prevent direct flows. We only want to prevent when the attacker is able to directly inject code information, because indirect flows from that where data elements indirectly influence the creation of code elements is something very essential to web applications. Take, for example, a wiki. There comes in wiki markup data, which is then translated into HTML markup. Therefore, this is the definition of an indirect flow from data into code elements. Therefore, we have to allow this, or at least in certain cases. And for this reason, we only have to concentrate on the star integrity axiom, which is responsible for preventing the direct flows from low to high. Good. So far, so good. Now we have to think about, okay, we talked about code elements and data elements, and now we have to get real and to say, what are, in our model, data and code elements? What we need is a mapping, something that we can apply from the concepts data and code to the single syntactic elements of the foreign syntax. So again, our SQL example. We decided to apply this mapping on a token level class abstraction. So we looked at a couple of existing foreign language grammars. So we looked at the HTML grammar, JavaScript grammar, SQL grammar, grammars for path and URL classification. So everything that is frequently susceptible to code injection attacks. And we derived general token classes from these grammars. And we derived 3 different classes. For one, those grammars have static elements. Static elements are tokens that are defined completely and statically inside the language's grammar. So select from where the language's keywords, and also meaningful punctuation, in this case star, equal, and dash. Those are tokens that are hard-coded, if you want to say this, in the language's grammar. Then you have identifier elements. In this case, the table names and the column names. Also something like variables, functions. Those are foreign syntax elements that are completely defined on compile time. So if you write a foreign code, you know which function you want to call and in which variable those data that you are computing should be ended up. So those are identifiers. The third class, obviously, are values. Values are, when you do foreign code assembly, usually differ from foreign code instantiation to the next. Otherwise, you wouldn't need a dynamic code assembly in the first place. So everything which values might vary on runtime. Strings, integers. In the case of HTML, the values of HTML attributes, and so on. So how do we map this now to the data and code abstraction? Everything that might lead to privilege escalation on the adversary side, so everything that might bring the adversary to more privileges than he has supposed to have on a syntactical level, if he influences has to be defined as code. So there's identifier elements and the static elements. And everything that should be okay to be defined by dynamic low integrity data is data, in this case, value elements. Okay, so putting this all together, we need for our type system, our expansion that we're proposing, we need, for one, we need new native data types that are responsible for representing the syntax and the foreign syntax elements within the code that the programmer writes. So we have we introduced code tokens and data token elements. A code token object instantiated represents exactly one syntactical token element within the foreign code. And we introduced the fleet as a really dumb mere container type, which represents the token stream. So a fleet just has a sequence of code tokens, data tokens, code tokens containing, for example, the keywords, a keyword, a punctuator, and or an identifier, a variable name, the data tokens containing all the values that are supposed to end up in the foreign code. Next, then, we need two integrity classes because we want to use the Biba model to formally ensure that we're doing the right thing. Therefore, we have two integrity classes, CT and DT. CT for code token is assigned to code tokens only. DT is assigned to everything else, to, for one, the data token elements, and also to all native data types that are provided or that exist within the native language. And by defining the subtype relationship, that code tokens are a subtype of data tokens, and using the subtyping and assignment rules from Parnell-Smith, we can prevent all direct flows from DT to CT. This is provable, and compared to more sophisticated type theory work, this is rather easy. So it's embarrassingly simple to prove that. Therefore, I spare you the details. But you can say this through through induction, simple introduction to the typing rules. And the bottom line is, as all data or all values that are controlled by the adversary enters the application through a native data type, and all native data types are implicitly typed with DT, they never can, in a code context that is typed with CT, and so they never can be used to instantiate code token elements. Finally, the model of the fleet. Fleet is a simple type-conserving container containing a dumb sequence of token streams. And thus, by implementing those types, data types and integrity types, we can ensure that within the native language, our data elements and our code elements are cleanly separated and will never be mixed up. Therefore, even if the programmer makes a mistake in what the way he's thinking, he's not able to create implicitly code tokens based on data tokens or data information that was given on runtime. And as the fleet doesn't do anything interesting but keeping the stuff and passing it on to the abstraction layer, within the native language, all data and code elements or tokens or types are cleanly separated without any means to dilute this separation. Good. This was our formal considerations. We did this mostly to ensure that what we're doing is actually provable or in a semi-provable way, doing that what we wanted to do. And now we come to our practical implementation that we did together with SAP Research. So in this, we talk about the language integration and the abstraction layer, which are more like engineering tasks. Our implementation target was, for one, HTML and JavaScript. So we wanted to prevent cross-site scripting attacks, or we wanted to aim at cross-site scripting attacks. Native language was Java. the J2E application server to be more precise. We choose cross-site scripting for the following reason. For one, cross-site scripting is ubiquitous right now. So there's hardly a single web application vendor that hasn't had a cross-site scripting problem in the last 12 months. And there's hardly a single open source or closed source application project that hadn't had a single cross-site scripting problem. So cross-site scripting right now is everywhere. And what makes it interesting from a viewpoint of assembling foreign syntax is that we have two distinct foreign syntaxes, HTML and JavaScript, that are interwoven and mixed rather widely within our foreign code. And also because the browsers are doing a rather good job parsing and displaying broken HTML, we have a lot of many non-trivial injection attack vectors that we would have to consider if one does defense otherwise. Good. Let's come to the language integration. This is a question, how do we, in practice, so we define what the properties of our fleet type should be. Now we talk about how do we fill it, how do we integrate the foreign syntax in the native language. There's a lot of prior work that we can rely on. I will discuss it rather quickly. So you can build an API, you can try to extend the native grammar, or you can use a preprocessor. So the API approach encapsulates the foreign code within API calls to, in this case, the fleet type, and the API calls then say the fleet type, okay, take this token, take this token, take this token. This is closely related to stuff, for example, like the XML DOM API, or something comparable has been proposed for SQL. This has some nice properties, so you can implement this rather easily for any existing application server, and you don't have to change anything, it's just a programming language. But you end up with a really ugly and cumbersome syntax, so that is so hard to maintain and debug that probably a no programmer will use this for non-trivial code generation. On the other side of the abstraction, this is something Microsoft has done really nicely, is that you can try to extend the native language's grammar. So in the LinkU project in Microsoft, they showed how to promote XML and SQL to be first-class members of C#, so that you can write in C# or any other .NET language just XML or SQL or SQL dialect to get to your data. So this is something you actually really want to do. So this is what the coders would like to do, and what also would serve our purpose really nice. You still have a strong mimicking of the foreign language's syntax if you do it right, but also you have stuff like good support for compile time checking if the foreign code is correct, and your programmers don't have to be trained that hard. The disadvantage is this is a rather heavyweight approach to solve this problem. You have to go rather deeply into your native language. You have to change your native compiler or the parsing process deeply. And also you have to do a more deep integration of the foreign data types to the native data types. So what have been done with LinkU. So I will be interested later on talking to people that worked on this, how feasible this is for other languages besides query languages and XML. The third path is somewhere in the middle. It tries to combine the advantages of both. Its usage of a preprocessor. So you encapsulate your foreign syntax within unambiguous syntactic markers, in our example, $. So everything that is encountered by the preprocessor, which is between $, markers, will be translated into a native API representation. So the programmer is more or less just writing the foreign code as he has used to, but it's translated into the internal API, and therefore it has the advantage of the API approach. This also has a couple of disadvantages that you have to live with. The biggest is that the code that is actually going to get compiled doesn't equal the source code, so it's not what the programmer wrote. And so if there are problems with the code that has been produced by the preprocessor, the error messages are really horrible. So if any one of you ever has worked with C++, I think you know what horrible error messages is, because C++ is exactly this problem. I think the rest is pretty obvious. Good for our practical realization, because we want to do something that we were able to do with limited resources. We choose, not very surprisingly, to use the preprocessor approach. So the preprocessor, so the programmer writes this source code mix between Java, HTML, and JavaScript with the syntactic markers. The preprocessor locates all the foreign code, parses it according to the foreign language's grammar, and creates the token type and the tokens, and translates all the foreign code tokens into the appropriate API calls that create the token objects within the fleet type. And this is how our API design ended up. So we wanted everything to be as explicit as possible. Therefore, we looked, also as required in our model, we looked into what are the strictest syntactic requirements for the single objects. So for the static code elements, like language keywords, tag names and stuff, there are dedicated API calls to create such types. Then there are limited dynamical calls to create identifier types, and the data elements just end up taking arbitrary data values because they are only data elements. Then there's an example for the preprocessor language. We still had to come up with a very, very simple meta syntax, because within the preprocessed code there has also been the opportunity for the programmer to include dynamic data values, native data values. This is translated into the Java API version, and through simple syntactic markers, native data types, in this case the native name variable, ends up as a data token within the fleet. Okay, furthermore, as I told you, we wanted to make the programmer a nice home. We built, again, a rather simple but powerful meta syntax for simple fleet operations, such as concatenation, combination, instantiation of fleet objects, which closely was mimicking the string operations, so concatenating two strings with characters. And also, we outfitted the fleet with from API that mimics the string API for splitting, searching, iterating over fleets. Finally, the abstraction layer. I go over this rather quickly because it's not that interesting, but it had to be implemented and solved. So if you want to build an abstraction layer which takes the fleet type and translates it into a representation that is understood by the external interpreter, you have to decide where to put it. You could put it into the native language and spit out here character-based representation. You can have something immediate, so that you have a couple of native languages all giving it the fleet type into the abstraction layer, and have a central point for processing the external language. What would be best is if you could include the translation process between the fleet type, which already contains the code in a pre-parsed, almost parse tree-like version. So a lot of the parsing process that has to be done in the external interpreter already has happened in the preprocess in the native language. So in the ideal case, we would just transfer the fleet information, and the external interpreter would use the data and code information within the fleet for secure operations. So like it is done with prepared statements, for example. In our practical implementation, because you can't do this in the browser, you would have to change the browser from accepting HTML code into fleet code, and we didn't have the resources to do so. Therefore, in our case, we built into the abstraction layer into the native language, which had the nice effect that we don't have any deployment problems. I will show you why in a second, because it was the J2EE, and J2EE was really nice in this. So the last step, the fleet has to reserialize, the abstraction layer has to serialize the fleet into a string-based representation of the HTML code. We did this because in this case, all our data contexts which we encounter in this case offer a possibility to encode data values into a non-executable representation. Therefore, we don't really have to think about what is in our data values. We just transform them into the representation that that prevents the browser interprets them as anything else as data. So with HTML entities, percent encoding, and within JavaScript, depending on the context, but usually with string from car code calls. This way, even if the attacker tries to trick us into including some syntactical elements that could be code, they won't be executed. Another avenue we kind of explored was comparing parse trees, as explained by Sue and Wasserman, but I skip over this.
Yeah, could you compare that? Compare with Sue and Suman's approach?
Oh yeah, this is so the observation that Sue and Wasserman made was really nice. I think I don't know how many of you know this. You obviously do. They said, okay, we have a string. If we compare the parse tree of the foreign code statement that we have with the parse tree of a foreign code statement that includes a code injection attack, then we note that in this case the parse trees differ. Unlike if the data placeholders in this parse tree only contains data, the parse tree is static from instantiation to instantiation of the foreign code syntax. But if you have a code injection attack, then the parse tree differs, and therefore by matching the resulting parse tree, you can see if a code injection attack has happened and if there's something that you should be concerned of. And this is really easy to do with our approach because we already know which of our elements are data. And by replacing the elements with dummy elements that reliably don't contain anything code-like, just static RR strings, you have two different parse trees, and if they match, you know, okay, no code injection attack has happened. What's it?
That is if you properly put out the notation for what's the data.
No, the Fleet type we already know which is the data. This is ensured and enforced by our data type.
Okay.
So we already know, okay, this is data and this is not data. And all here we have to think about it is how do we treat the data within the Fleet so we don't introduce in the last minute injection variable. So this is pretty much implementation. Yeah.
It seems that your Fleet approach is an instantiation of the Sue and Wasserman technique.
No, I don't think so. Sue and Wasserman, as an implementation, relied on dynamic tainting. So Sue and Wasserman still rely on a string-based code injection, a string-based code assembly. The only thing that resembles is when we use in the abstraction layer at the last moment. If we look here at our resulting Fleet object and the contents, then we can use their mechanism to see if somebody attempted to do code injection attack.
Maybe we should take this offline, but I guess my perspective is that Sue and Wasserman required the parse tree to remain the same. It shouldn't change when there's code input, when user input is inserted.
Oh yeah, it's totally comparable. Otherwise, I wouldn't have mentioned it here. So they're
And you're limiting to the case where the parse tree doesn't change with respect to just data or code, and you have a much coarser notion of what a parse tree is.
I do and they do.
You do.
No, I think we have a finer grain, because one of the things with the Sue and Wasserman approach is that if the attacker is able to influence the identifier elements of your code, for example, the table names of your SQL statement, the parse tree doesn't differ. So take an example which is not that contrived, that depending on the execution context, the prefix of a SQL table that you access differs. So admin users versus regular users. And the prefix is controllable by the attacker so that he can change the user prefix to admin prefix because of some logic error within the application. Then he's able to do some privilege operations on the admin user table without changing the parse tree. In our approach, something like that is not possible because we can treat and identify elements to be code, and they are not accessible to the or not definable through dynamic data at all directly.
or something.
Yeah. Okay, implementation. Implemented this together with SAP Research as a J2E filter, providing a fleet interface, and the legacy string interface just went to a log file so that we can ensure that no legacy insecurely generated code ends up within the HTML code. We did an evaluation. We evaluated the protection properties of our approach by creating a really insecure test servlet, blinkly echoing back attacker-provided data into different foreign code contexts, and ran a list of well-known evasion techniques against this servlet to ensure that none of the attacks actually happen. We also verified that our approach is usable in a real-life scenario. Therefore, we took a mature, rather large J2E application, in this case a J2E wiki, and adapted it or rewrote it to use our fleet semantics. JSP wiki had about 70,000 lines of code and seemed to be a good evaluation target for a couple of reasons. For one, it contained the version that we used, contained a rather large number of different cross-site scripting problems, stored cross-site scripting as well as reflected cross-site scripting. Because it's a wiki, it contains a lot of non-trivial generation of dynamic HTML content. And for performance evaluation, it doesn't have to use a database backend, or it's optional. Therefore, when we later do our performance evaluation, we don't evaluate the database performance, but actually our implementations. We ported this JSP wiki to our fleet approach. Out of the 365, about 103 or plus minus 1 or 2 files had to be touched. This took me, so I did the porting, and it took me about a week, so it wasn't that hard. Also because JSP wiki is rather well written, so with a badly written application it will take considerably longer, because you have to take every single string element in your application and you have to decide, will it ever end up in a code context? Will it ever be used to generate HTML? And if so, you have to translate it to the fleet semantics. The result was that all the cross-site scripting problems that were in the application were resolved after porting it to fleet without even looking where in the code those cross-site scripting problems were. We just ported it, and afterwards verified those cross-site scripting problems were gone, just because we now use a different paradigm to build the front code. Okay, we did a performance evaluation with standard means, and ended up with a runtime overhead between 10 and 25%. What I thought was, for a reliable security, okay, on first implementation of the approach, okay result. Good. Let's come to the conclusion. So I hope I have convinced you. Otherwise, I'm looking forward to the discussion that using our approach, we reliably prevent string-based code injection, so that the programmer, even if he tries to write insecure code, shouldn't succeed so, because we don't have any a path from unsecure string data to code token objects. Using our practical implementation, we've shown that it can be easily implemented for existing languages, frameworks, and application servers. We allow. So it doesn't really matter how complex the foreign syntax is. A complete coverage of the foreign syntactic elements is achievable rather easily using our approach. You only have to identify, using the foreign grammar, which are the static and the identify elements. Everything else comes pretty much naturally. And therefore we can apply it to arbitrary foreign languages types. So we can use model query languages, markup languages, general purpose, and more interesting hybrid languages such as HTML, JavaScript. And furthermore, that might be subject of future work. So building a preprocessor, an API, is pretty much dumb. So it's really straightforward if you have a grammar and a mapping between elements of the grammar and the data code categories. Therefore, based on parser or compiler approaches that already exist, automatically generating for a new foreign language an API and preprocessor can be rather easily automized. So, because it's pretty much just take the token elements, translate them into API calls, and pass the existing code for a preprocessor markup. Okay, so with this I conclude, and maybe looking forward to some discussion.
Which values in the language have high integrity and which have low integrity? Like, is a string literal automatically high integrity?
No, all values are low integrity.
Okay.
So the only high integrity things are static elements or semi-static elements of the foreign syntax. So all the keywords. So basically everything that the attacker want to control, let the attacker control to prevent code injection attacks, you define to be high integrity.
So it's not a matter of how things are manipulated in the program. It's the string values themselves. Like Martin would be low integrity, but select would be high integrity.
Oh, the string select would be low integrity as well. Only the token. So we have this two new native data types that represent foreign token elements within our language. So.
I saw in some of your examples, you said things like new fleet, and then you pass in the string select.
I see. I should get rid of this example. You're right. This was just an example of a dumb API representation of a preprocessor, but it wasn't a fleet example. So the good point. Let's go back to the
output of the preprocessor, right?
No, wait a second. We go back to this. So the output of the preprocessor is here, and it should be, if I haven't screwed up, should be adhered to the requirements that are formulated. See, so in this case, in the example above, we have a code token, that's the B tag. We have a data token, it's the hello string. We have a data token, it's a dynamic string, and we have another code token, it's the /B tag. Translated into the foreign language, into the API. We have a static call that creates a code token object for B. Then two calls that create data tokens for the strings hello and for the dynamic string. And we have a last API call that again calls a code token for the closing B. So in this case, we don't have any data flows from low integrity string data to high integrity code tokens.
So there has to be a finite number of high integrity tokens so you can generate those.
Yeah, because the static elements in your native language, in the grammar, in the foreign language's grammar, the static elements are finite, and therefore you have a finite number of API calls that create those things.
So doesn't that generate some sort of a syncing issue?
What is syncing?
Well, where, if your language is evolving, right, you need to then sync new keywords into the preprocessor.
Oh yeah, you have to expand the API if you have a new language version. But this is rather lightweight. So adding a couple new API calls is really easy compared to if you go with what I outlined, the approach where you try to include the foreign grammar or the foreign syntax into your native language, where you have to change your complete parsing process.
Isn't that a management issue then? I mean, that you have to then make sure that you have the right versions?
I think you always have management issues in this direction, sure.
Yeah.
But I don't think...
It just adds another one to all the ones we already have, right?
But so you have to wait. Do you want to... If you want reliably secure code, you might
I get that.
want to pay the price.
That, because not only do you have to make sure that the programmer's okay with this, right? You have to make sure your IT people are okay with it too, because they're installing it.
Oh yeah, I think that the programmers shouldn't be this big a problem. The bigger problem might be the people that have the deployment requirements, because they have the work to do. For the programmer, if you look at this, I think this is a rather good example, because you see, for the programmer, it doesn't really change anything. If he has now double quotes or or dollar syntax, it's the same programming paradigm that he uses. So it's pretty much as he would still use strings, but in a secure way.
So this dollar syntax is what you added to the original code?
So this dollar syntax here is our represent the syntactic markers that tell the preprocessor, okay, here starts foreign code. So everything else, the preprocessor goes through the Java code, and whenever he encounters such syntactic markers, he starts the parsing process and translate what is between such syntactic markers into the API representation, then creating the token object and the data token object.
So that's the marking that it's a foreign code?
So between so the foreign code, the dollar sign is just our meta syntax. The foreign code is the HTML code that is embedded into the Java code.
So again, this is more of a band-aid as a quick fix scenario, right?
No,
Because going forward, you really want to have this in your native.
Oh yeah, sure.
More than anything else.
Yeah, I think I've thought this. So this is pretty much, this is something feasible. So you can do this rather quickly and rather reliably. But so if you're able to pull this off for really complex languages and with good language coverage, you should go the path and extend the native language, the way the LinkQ project here in Microsoft is doing it. I think this is remarkable work.
So with a language like JavaScript that has a dynamic evaluation feature where you can
this is
execute it,
yeah.
is the pre-processing as straightforward, or do you need to kind of recursively invoke the preprocessor every time you hit eval?
To solve those problems, so eval is a big problem for stuff like this. So to solve those problems, you would need to add a fleet abstraction within the JavaScript language. So this is out of scope for a solution.
Every time you got a new script, you would have to essentially do another pass.
So this is, eval is a problem. I think usually eval is a problem.
You still have the problem here, right, if that when you generate code from this HTML flat, that it could be interpreted as a browser as JavaScript because of encoding tricks. I submit a parameter that's a name, but it's actually could be interpreted by the browser's parser as JavaScript.
So yeah, if you don't implement your the final serialization step, if you make mistakes there, then obviously yes, you can.
The HTML flat serializer that you implement has to emulate the behavior of all browsers, right?
I think there are a couple of. So if you choose to encode all text elements in this non-executable representation using complete HTML entities, I don't think there's any evasion technique that the attacker could use that would break that to include HTML markup or JavaScript markup. You only need the only thing that the abstraction, especially with HTML, so all the evasion techniques usually confuse the sanitation process within the application by two general techniques. The one is giving totally broken markup that can't be understood by the sanitation project and therefore produces errors, or otherwise confusing the sanitation process in which specific code context a certain data value is injected. Because it's totally different if you have a data value injected into HTML context, into URL context, or into a JavaScript context. And in all those contexts, it's essential that you use different encoding techniques. But so the first thing attackers use, so the broken or obfuscated HTML markup, can't happen because all the markup that is supposed to be or that will end up in the code later on will be generated out of our code tokens. So this is the first thing. The other thing, so all HTML is created explicitly. And the other thing is that because we already know which HTML tags or which code context we are, because the fleet contains everything in a pre-parsed form, we can reliably ensure that we know in which context we are, and therefore we can reliably choose the correct encoding method, HTML, entities, URL % encoding, or JavaScript encoding.
Right, you showed that on a slide, right?
Yeah.
Didn't show that. So you had a string.charcode@.
Mm.
What was that? I don't remember what that was.
Say it.
Can you try and find that slide?
I can too. I can try. That's sure I find it.
From charcode, that's right.
Yeah. So it takes an integer value and translates it to characters, and therefore,
Doesn't that create quite a bit of JavaScript?
sure, it does.
Right, 100 characters equals a magnitude more.
Oh, it doesn't. So, yeah, it bloats up your code by 0.03. So because you can have separated the values here with a colon, and so it's not that bad. Yes, your resulting HTML code gets bigger, but also our internet connections get faster.
Right? It's like 4 to 1.
Yeah, I can live with that.
A little less than 4 to 1.
Yeah, security comes with a price.
Yeah. Sure, we had lots of bandwidth. Let's go for it.
So Martin will be available tomorrow tomorrow morning.
Oh yeah.
If anybody wants to, anybody who hasn't met Martin wants to talk to me more about various other things, send me a bit.
Great. Thanks.
Thanks. Thank you, Martin.